Did you know that conservation of energy is in fact not always conserved?
What?
Yes, quite strange, isn't it?
What do you mean conservation of energy is not always conserved? Of course it is.
Well, why do you say that?
Well, that's what my textbook says.
Yes, and some textbooks still say Yugoslavia is a country. Sometimes textbooks are either wrong or outdated, saying, why are things conserved in the first place?
Because we measure it.
Sure, but the theorist in me is unsatisfied with the inelegance of mere measurements. Surely, there must be some theoretic justification.
Is there some theoretic justification?
Glad you asked.
This might have been a bad idea.
Do you know what a symmetry is?
Yeah, it's something about when the reflection of something is identical to the original thing, right?
Correct. But more broadly, you can say it is any transformation which leaves the original system invariant.
But invariant how? Things can look identical in multiple ways?
Good point. Here, we are interested in transformations which leave the Lagrangian invariant.
Like what now?
Lagrangian. It is a physical quantity defined as the difference between potential and kinetic energy.
Okay, but why this specific thing?
Because of Noether's theorem, proved and published just over 100 years ago, Noether's theorem is the key to our question. The math is pretty involved and requires Lagrangian mechanics, but the text of the actual theorem is deceptively simple. A conservation law implies a symmetry, and a symmetry implies a conservation law. That means if you measure a conservation law, there must be an associated symmetry somewhere, and if you find a symmetry, there must be an associated conservation law.
That's pretty neat.
Exactly. That's also why your physics teachers are obsessed with symmetries and symmetry breaking.
So, does that mean conservation of momentum is associated with a symmetry?
Exactly. Space translation. If you performed an experiment in space and shifted everything 30 meters to the right, that doesn't change your experiment, and hence momentum is conserved.
But, when is that not true?
Here, nothing was part of the frame, so shifting doesn't change much. But consider electrons inside a crystal. To make calculations easier, we imagine that electrons are moving inside a periodic potential, which is part of the background. But now something interesting happens. If we translate the electron, unless the potential is constant, its potential energy will change, and so will its Lagrangian. Thus, the translation symmetry has broken. However, since this potential is periodic in space, if the translation is by the spatial period, the Lagrangian will again be invariant. So here, there is a discrete symmetry rather than a continuous one. Instead of momentum, something called crystal momentum is conserved.
So momentum is not conserved in crystals?
Well, that depends. In the previous frame, that is correct. But if rather than letting the potential be part of the background, it is generated by particles, which are also shifted in a translation, conservation of momentum is restored.
Okay.
Yeah, some conservation laws are quite specialized.
But hold up, you said conservation of energy is violated, so explain yourself.
Well, first we need to find the associated symmetry. To save you some Lagrangian mechanics, it's time translation.
What?
Whether you do an experiment now or in 10 days doesn't matter.
Actually, I do have deadlines.
Perhaps, but the universe doesn't care about the time. Or does it? I told you conservation of energy doesn't always hold. So somewhere, or at some scale, time translation is violated.
Is this another quantum thing?
No. Virtual particles are neat, but that is not what I'm talking about. Think bigger. What if you were to perform your experiment 15 billion years ago?
Well, that would be difficult since that is before the Big Bang.
Exactly. The universe is expanding, or changing, over time.
Well, that's neat, but do we have any tangible evidence for that?
You bet we do. Billions of years ago, right at recombination, the cosmic microwave background was emitted. However, we know that the CMB must have originally been in the visible spectrum, but today it is in the microwave spectrum. Since the number of photons has stayed constant, each photon must have lost energy.
That's actually kinda cool. But what's the moral?
If you must have one, I guess be aware of your basic assumptions? But why do you ask?
All good tales end with morals.
Huh, I guess you're right.